All right, we are ready. Good morning. I'm just gonna grab these notes. So like I said, I'll adjust these. There's no way we'll finish these today, but because we still have some work to do in chapter 2. Create new note in, here is this class. It's thinking. All right. So last day was a big day. Got something in my eye. Got it. What did we do? We talked about combining functions, either algebraically or through compositions, right? So combining functions either algebraically, so that's things like f plus g, f minus g, f times g, and f divided by g, right? If we have two functions, f and g. We could also, I'm not going to say compositionally, but through compositions, like f composed with g. Maybe I'll do this because this one's important. F composed with g of x is the same as f composed with g of x. So wherever you see an x, you're going to evaluate f at g of x. So you get f of g of x. And I find that this is actually the easier way to read these function compositions, right? So, but you should be able to recognize f with a little empty circle of g. We can read it as of, or technically it's f composed with g of x, right? And so we're creating these new functions, whereas f composed with f of x is also a thing. So that's when we put f of x into f of x. Makes it bigger, typically. So then we went on to talk about one-to-one functions. One-to-one functions. We need one-to-one functions. Actually, this is not part of combining functions. So maybe I'll scoot it over a bit, mostly because I need more room. So one-to-one functions. A function is one-to-one if we can show that f of a equal to f of b, right? So we evaluate the function at a and b and we set them equal to each other. So if we can show that if this is true, that f of a equals f of b means that a equals b in the end, right? Then we have a one-to-one function. Hey, it's frozen. So then we have a one-to-one function. Why do we care so much? We need a one-to-one function in order to find the inverse. Only one-to-one functions are invertible, right? So to find the inverse. So here, we need a one-to-one function in order to be able to find the inverse. Able to find the inverse of a function, right? So that only works if we have a one-to-one function. So usually that's where we start. show that this function is 1-to-1, and then I ask you to find the inverse, and then I get you to confirm the inverse. But let's talk about that. So if a function is 1-to-1, if a function is 1-to-1, we find the inverse. We find the inverse. And we had a couple of different ways of doing it. I'm going to stick to my way where I switch the x's and y's immediately, because then I don't have to remember to do it later, because that could mess me up. So if a function, or I mean, mess you up, but if a function is 1-to-1, we find the inverse by, your first step is going to be to write y equals f of x. Okay. Your second step is to exchange x's and y's. Okay. Once you've exchanged them, right, so now you're going to have, so y equals x minus 2 over 3 plus x, something like that. You've exchanged them, so now you have, well, now I can't remember what I just said, but x equals y minus 2 over y plus 3, or whatever I said before. So you exchange your x's and y's, and then your third step is to solve for y. The final result is the inverse of f of x, which we denoted by f, and then on the f we have a little to the -1 of x. It's really important that you put it on the f, right? F of x to the -1 is just 1 over f of x. That's not what we're doing here, right? The inverse is something different. And then we confirm that this is the inverse by the cancellation properties. Use the cancellation properties to show that the inverse you found is indeed the inverse. By showing that f composed with the inverse, you end up with just x, and the inverse composed with the function, you have to end up at x too, or as well, I should say. Okay. That's a lot of stuff that we did last day, but it does make for a really nice test question, right? So I give you a function, I ask you, is it 1-to-1? So show me that it's 1-to-1. Then find the inverse, then show that it is the inverse, right? And so that means we incorporate all these function compositions, right? A lot of algebra. And so this makes a really nice test question, right? Because it incorporates the function compositions. But what's nice about it is that you always know you have to end up at x. And so it is also a way to make sure that the inverse that you found is actually the inverse, right? And so it's kind of like a guaranteed, check your work, make sure everything is right. And then, yeah, so it should be kind of safe marks. It's a lot of work, right? But it should be pretty safe since you're checking your work at the end. Okay, where were we? So just to continue the review, because what I realized was, and asked if we were able to have a break. Yeah, I guess. I mean, you can have a break whenever you want. But yeah, just remind me whenever you want it. I can blah, 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 blah. But yeah, that's probably good. Let's do that. Where were we? Oh yeah, so what I realized is we didn't actually show that the first function was one-to-one that we used, I think. Either way, let's pick up where show that, so this is still part of the review, that f of x equals x minus 2 over x plus 2 is one-to-one. So what do you have to do? Well, to show that something's one-to-one, right? First thing I'm going to do is I have to set up f of a and I have to set up f of b, right? And I have to set them equal to each other. And then hopefully with cancellation and just kind of moving things around, I'm able to end up with just a equals b. In this case, because I know I'm asked to find the inverse, they have to be one-to-one. So I know that I have to end up here. Right, and that's going to be the case on a test as well, right? So I have to start with f of a equals f of b. Notice that I put it in the middle because I usually fill it out going outwards like this. Okay. So f of a is a minus 2 over a plus 2. F of b is b minus 2 over b plus 2. So if we're going to simplify this, right, the easiest thing to do is just to multiply b plus 2 over to the left-hand side and a plus 2 over to the right-hand side. And so a minus 2 times b plus 2 is equal to b minus 2 times a plus 2, right? And I'll just show with little arrows here where things are going. Oops. Okay, so if we expand this out and expand this out, because my goal is to simplify this thing, so I'm going to expand things out and hopefully things will cancel. They will, if we've done it carefully, right? And so a times b is ab, a times 2, so plus 2a minus 2b, and then negative 2 times 2 minus 4. And this is going to be equal to AB. Notice that I wrote it as AB. Here we would probably write B times A, but because I want to be able to cancel and see it quickly, then I'm just going to write AB. Plus 2B minus 2A minus 4. What I do is, and there are a lot of different things, right? You could try to put all your B's to one side, A's to one side, right? You've got B over here, B here, B here, B here. You could do that. I like to just shift everything over to the left-hand side and set this equal to 0. And then it's easier to cancel stuff, I find. Okay. So what we get is AB plus 2A minus 2B minus 4 minus AB minus 2B plus 2A plus 4 equals 0. Careful when you bring this over, right? Minus AB minus 2B plus 2A plus 4. Okay, so now AB minus AB, that's nice because that would be hard to deal with if we're trying to show that A equals B. So those cancel out, so that's great. And then also minus 4 plus 4 is going to go away. Looks like I have 2A plus 2A, so that's going to be 4A. And then minus 2B makes minus 4B. So I have 4a minus 4b equals 0. I'm going to move this minus 4b over to the right-hand side, so I get 4a equals 4b. So A is 4B divided by 4. 4 divided by 4 is going to cancel, and so finally A equals B, which means, and I always want you to have a little kind of summary what that means. Therefore, f of x is 1-to-1. Last day, we found the inverse of this thing, right? So last day, we found, now let me just go steal it here. We found the inverse was this, quick copy. Okay. And we also showed, which one did we show? Which version did we show? And we also showed that f composed with the inverse, right? So plugging in the inverse that we found here into the original function puts us at x, right? So, and we showed that f composed with the inverse, oops, maybe I'll scoot this over a bit. Okay. We found that the inverse is that, and f composed with the inverse of x equals x. Okay. So this is the kind of where we ended off last day. So we will now continue to show that the inverse composed with the original function is also equal to x, right? That's going to be a nice warm up for compositions, and then we'll do another one where we have to find the inverse again, just for a refresher. And then we'll move on to chapter 3. All right, so let's see here. We've got our function up here. I'm just going to keep it. Where should I keep it? Just because we'll need it. Okay. So here, I'll put it in a little box so it's separate. Okay. So we were able to show that the function composed with the inverse is equal to x. So now we're going to do something similar and show that it is also equal to x, because otherwise we didn't find the inverse, but we did, so it's okay. All right, so the inverse composed with the function, well, wherever I see an x, I'm going to replace it with f of x. And so what I'm going to have is the f inverse of f of x is going to be -2 times 1 plus f of x all over f of x minus 1. So now I need to squeeze in f of x is x minus 2 over x plus 2. So what I'm going to do here is I'm going to have -2 times 1 plus x minus 2 over x plus 2. Just going to use brackets, more brackets than I probably need, just to make sure that everything kind of stays together. Over x minus 2 over x plus 2, sorry, minus 1, that would be a fatal mistake. There. So now I've got 1 plus a fraction and then a fraction minus 1. I'm going to need to find a common denominator for both of these. What's nice is that they're the same common denominator, right? So eventually they'll cancel out. But we need to show all our work to get there, right? So I'm going to multiply 1 by x plus 2 and then this 1 by x plus 2 over x plus 2, of course. So here we go. Negative 2 is on the outside, so I'm just going to leave it for a long time here. 1 times x plus 2 over x plus 2, right? Forcing that common denominator, plus x minus 2 over x plus 2, divided by x minus 2 over x plus 2, minus 1 times x plus 2 over x plus 2. All right, so now I can simplify. I can write this over the common denominator and I can simplify the numerator. And so I get negative 2 times x plus 2, oops, I'm not going to use those brackets anymore. X plus 2 plus x minus 2 all over x plus 2, oops, divided by x minus 2, and then I have to be really careful because I'm bringing in a negative 1, right? So minus x minus 2, so minus x minus 2 divided by x plus 2. So now I can simplify this a little bit, right? I get x plus x and I get plus 2 minus 2, so those are going to cancel out. Plus 2 minus 2, and then I have x minus x, but then minus 2 makes negative 4. And so what I have is negative 2 times 2x over x plus 2 divided by negative 4 over x plus 2. Yeah. I've got a fraction over a fraction, which means I have to flip and multiply, and that's when I'll be able to cancel these x plus 2's, right? That's when they're going to cancel out, but not until then, so you have to be really careful. Negative 2 times 2x over x plus 2 times x plus 2 over negative 4. Okay. The x plus 2, this is where I can show that they cancel. Now, there's a couple of ways you could expand this in, right? So then you get negative 4x over negative 4. Either way, things are going to cancel, right? And so you get, this becomes negative 4x over negative 4. And once again, I'm just going to keep it on the same page here. So I've got a page break here. I don't want it floating around. So here, woohoo. So now we've shown, right, that because we already were able to show that the function composed with the inverse is equal to x and the inverse composed with the function is equal to x, right? We've proven that this is the inverse of this function. Right? Therefore, f inverse of x is indeed the inverse of f of x. Okay, so let's see here. Let's do another one, kind of start to finish. I'll go grab these, where were they? I think, yeah, here. So we've got a couple of options. Just as a heads up, some of these restrict the domain. So remember last day we said, okay, well, even functions, so functions with even powers of x, they're not generally one-to-one. So when you see an x squared like this, or an x squared here, or x to the 6, typically what we have to do is we have to restrict the domain in order for it to be one-to-one. Was that example from the notes? It was this one here. Pretty sure. X minus 2. Yeah. Just want to make sure. Yeah. I know. Notes everywhere. All right. So all of these fraction ones, right, are going to be very similar to what we just did. The ones that where we restrict the domain, you're welcome to graph it and kind of see, okay, if I restrict the domain, it should be one-to-one. And I think we mentioned it last day, but it's okay. I'm not going to make you do one where you have to restrict the domain on a test. So I'm not going to spend any time doing that one. But let's see, which one do I want us to do? We did a fraction one. Maybe let's do a square root one. So kind of a typical, my iPad keeps freezing up. So let's do 68. F of x is 2 plus the root of 3 plus x. Okay. So we've got a restriction on the domain, right? We can't take the square root of a negative number. And so we're going to keep that in mind because one of the other properties of the inverse is that the domain of the original function and the range of the original function, they switch places for the inverse, right? So the range becomes the domain for the inverse, and the domain becomes the range for the inverse. So we're just going to keep that in mind. It's not going to really bother us, right? First thing we're going to do is I'll make part A. Show that f of x is one-to-one. Okay. So here I'm telling you this thing is one-to-one, so you should be able to find that it is one-to-one. And so what we get is, well, we start here, f of a equals f of b, right, to show that it's one-to-one. And so we get 2 plus the root of 3 plus a is 2 plus the root of 3 plus b. Make sure my b's don't look like 6s. Still kind of do, but we know what it is. So now what I'm going to do is, oh, what can I do? I can subtract 2 from both sides. So then I get 2 minus 2 plus the root of 3 plus a is the root of 3 plus b. Well, 2 minus 2, of course, goes away. Got rid of those. And so the root of 3 plus a plus the root of 3 plus b. So the root of 3 plus a is the root of 3 plus b. If I square both sides, right, and I'll show that in blue. then those square roots go away, right? So now I have 3 plus, oops, 3a, something completely different. 3 plus a is 3 plus b. Now, I'm so close, right? I can subtract 3 from either side. And so 3 minus 3 plus a is b. Well, this, of course, goes away. And now I'm left with a equals b. Therefore, right, always kind of link a conclusion to this. Why did we do all this? Well, it was to show that this thing is one-to-one, show that f of x is one-to-one. Therefore, f of x is one-to-one. I know at this point you're thinking, or you're probably thinking, I'll never use this. Why would I care if a function's one-to-one or finding the inverse or the compositions? That's not why we're doing this, right? It's not so that you are really good at showing that something is one-to-one. It's to get you really good at working with algebra, right? And so these are just really good exercises for working algebraically, right? So being able to boil this down into something like a equals b, it's nice because it's a safety net. You know you have to end up at a equals b. And so this is a really good kind of test run to see how good your algebra is. And algebra is just math, right? Where we're kind of switching things around. You should be able to, well, I would exclude the ones with the ranges. Don't worry about those. You should be able to go through and show that each one of these is one-to-one, right? Same thing, you should be able to go through each one of these and find the inverse and do the function composition. That's a lot of work, right? But I want you to be really kind of comfortable with shifting things around and solving for values, because it's going to be really important in your other courses, right? Not necessarily finding one-to-one functions and showing the inverse and that kind of stuff, right? But we're just warming up. Okay, so yeah, I realized that as I was doing this one, like, they're probably thinking, I'll never use this. When would I need this? You won't, but you do need algebra. So that's why we're here. All right, so we've shown that this thing is one-to-one. That's great. So now, oh, nice. Tim mentioned that inverse theory is used in industry a lot. So that's really good, actually. Thanks, Tim. So we've shown that it's one-to-one. Now we're going to find the inverse. So part B, I'll put it on the next page. Find the inverse of f of x. Okay. All right, so the inverse of f of x, remember, is f to the -1 of f of x, or of x. But what we do is we start with, and you know what, I'm going to put the little steps here. We've only done 1 or 2, so or potentially only 1. So let's start small here, right? The first thing we have to do is we have to write y equals f of x. So what that means in our case is we have y equals, and our f of x was 2 plus the root of 3 plus x. And you know what? I'm going to scoot this up here. Our second step, just so it's not so long, is we're going to exchange x's and y's. Okay. So what that looks like in our case is, well, I'm going to write x equals 2 plus the root of 3 plus y. In this case, there is only one x and one y. There could definitely be, just like we saw earlier, there could be more than one x, which means you would have more than one y. Arguably, this function is easier than the one we just did with the fractions, but it's different, so that's why I wanted to do it. So now, once we've exchanged x's and y's, then I'm going to solve for y. So step 3, solve for y. The final result is y is the inverse of f of x, right? So this y is going to be the inverse, unlike this y, which was the original function, right? But it's because we've done the switcheroo. So that can be kind of tricky to keep track of. X is 2 plus the root of 3 plus y. So if I'm trying to solve for y, I'm trying to get y on its own. So slowly but surely I have to move things over here. So x minus 2 is the root of 3 plus y. To undo the square root, I have to square both sides, making sure that I square x minus 2. So this becomes x minus 2 squared is the square root of 3 plus y squared. This square is going to get rid of the square root. I'm probably just going to leave it as x minus 2 squared here. We'll see if I end up expanding it. Remember, x minus 2 squared is x minus 2 times x minus 2. You want to be really careful. So what we get here is we get x minus 2 squared is 3 plus y. So solving for y, I have to subtract 3 from both sides. Usually what I'm solving for, I like to have it on the left-hand side. Remember, the equal sign is really just a revolving door. So what I'm going to do, and this catches people off guard, so that's why I'm mentioning it, is I'm going to write y equals x minus 2 squared minus 3. All I've done is I've subtracted 3 from both sides, so I've moved it over to the left-hand side, and then I swung it around to get y equals x minus 2 squared minus 3. Okay. Only because I like to have the y on the left-hand side. Okay. So therefore, f inverse of x is x minus 2 squared minus 3. Okay. So now we have the inverse, and now we're going to make sure that this is the inverse by using the cancellation properties. So now, part C, show that the inverse you found, or the inverse we found, let's say, not put you out on your own, show that the inverse we found is indeed the inverse. Okay. What does that mean? We'll use f composed with the inverse of f of x, or what I should say is show that the inverse, or the function composed with the inverse and the inverse composed with the function, they both equal x. We have to show both. Okay? Very tedious, or it can be very tedious. I'll start with this first one. F of the inverse of f of x is equal to, well, the function, let's remind ourselves what our little function was here. Whee. Copy. So I'm going to paste this here, And I'm going to move this down to the next page here. I'll say recall, and then I'll bring the inverse over as well. Or what we're claiming to be the inverse, we might find that we did something wrong once we try to show that the inverse in the function doesn't become x. If that happens, right, something probably went wrong, right? Try it a couple of times, but something might have gone wrong in finding your inverse. So then you'd want to go back and check your inverse. So hopefully things work out. F of x is 2 plus the root of 3 plus f inverse of x. Okay. And f inverse of x is x minus 2 squared and then minus 3. So we get 2 plus the root of 3 plus, and I'm going to put my whole inverse in brackets, right? Especially because there's some subtraction going on here and I don't want to lose anything. So I've got x minus 2 squared minus 3. Okay. So looks good, right? Because I'll be able to cancel 3 minus 3 is going to go away. So that's going to clear up some of that square root. So now what I've got is I've got 2 plus the root of x minus 2 squared. Well, the root of x minus 2 squared, remember exponent laws, right? The square root of something is really that something to the power of 1/2, right? 2 times 1/2 is just 1, so that's why they cancel. But I'll just kind of show it like this. And so 2 plus x minus 2 is really 2 minus 2 goes away, x. Yee. It's a good feeling, right? What does that tell us? Well, it tells me that this inverse that we found is probably the right inverse, right? Because if we're able to show that one of them equals x, then the other one should equal x as well. So let's go ahead and do the inverse composed with the function and just make sure that they are. So now the inverse composed with the function, the inverse is x minus 2 squared, so that becomes f of x minus 2 squared minus 3. F of x, gotta keep it on there, and I'm putting everything in brackets. Sometimes I don't need them, but I'm better safe than sorry, right? So 2 plus the root of 3 plus x minus 2 and then squared and then minus 3. Looks like I'm going to have the same type of situation where 2 minus 2 is going to go away, and then I'm squaring the square root. That's the whole idea of the inverse. The inverse just kind of inverts the function, right? So it's the way of undoing it properly. So, uh-oh. Hey, I just charged it like very recently. 2 minus 2. It's going to go away. And so we've got the root of 3 plus x to the power of 2 and then minus 3. Again, square root and then squared just goes away. So then we have 3 plus x minus 3. But of course, 3 minus 3 goes away. So we get x. Okay. So therefore, right, since we were able to show that both of these equal x, right, show that the inverse we found is indeed the inverse, therefore, f inverse of x is indeed the inverse of f of x. Whee! And it's okay, it can be generic like this. Sometimes I'll put the actual inverse function in the function, but by this point, you're just happy you're done, right? So, but I do want to see some sort of kind of summary here, right? You have to answer the question, is it show that the inverse we found is indeed the inverse? Well, here we showed it, and so we can say that there. Yeah, they are long questions. Yeah, Logan says, gotta love using an entire notebook page for one question. I write so big, it's usually 2 pages, but makes you feel good though, right? Oh, where was it? Oh, these pages. Okay, so just as a little note before we get out of inverses, I want you to work on those, right? Definitely, because it is really, really good algebra practice, but these 49 through 69, because this one has an interval, right? Don't worry so much about the ones with restrictions on X, right? So don't worry too much about those. You can try them on your own time, but I'm not going to test anything like that, right? For a test, truth be told, I'm probably going to stick to something with fractions. Oh, nasty, right? Definitely try these too, but yeah. So that's why I started with a fraction one. Right, so for tests, probably something like 54 through 60. Okay? So definitely the least amount of work to prepare would be doing all of 54 to 60. Right? Showing it's one-to-one. Find the inverse. Show that you have indeed found the inverse using the cancellation properties with the function composition, right? So to prepare for a test, I don't know, I don't think we've talked about a test, and I'm looking at the schedule here. I think I want to get through chapter 3 before we have another, or chapter 3, rationals and polynomials, before we have another test. What's nice about this next section that we're about to start is we're going to head back over and kind of smooth out some of the things we talked about in the fundamentals, right? So rational expressions, for example, right? Kayla's asking, are we still doing 3 midterms, or can we vote again? Well, I'm open to suggestions. Are you guys totally swamped with tests, probably? I was gunning for 3 midterms because that's what we said. Everyone's just sick of midterms. No one wants to do them anymore. All right, I'll keep that in mind. Everyone's all burnt out. One midterm. The one we did. Yeah, I wish. It'd be great. We'll see what we can do. Okay, so I'll see if I can figure something out that's kind of less midterm heavy for you guys, but no promises. Yeah, less work for me. Yeah. So to prepare for a test, that's what I wanted to say here. The assignments are posted on Moodle. The links should be there. Has anyone been able to try them? When I try those links, it says I'm not allowed to go in there because I'm not a student, which is really stupid, but so I can't actually test drive them. But if someone, I haven't checked to see if anyone's been in there yet, but anyways, I'll check in with you guys. But you do have a couple of quick assignments from section 2. Oh, nice. Okay, so yeah, they're in week 7. Awesome. So they're working, great. And they're just little quick ones, except for the first one. 2.1 is a biggie, and then I think a whole 10 questions or something. So just to kind of touch base. Awesome. So to prepare for a test, do 54 to 60, and then 65 to 69, kind of less important, right? And A, show it is 1-to-1. B, find the inverse. C, confirm the inverse, just like we did below. Okay. Definitely some sort of test question coming at you. So just to prepare for that, just work through those problems. Okay. All right. I guess we can do a little break before we head into the rational and polynomial functions, polynomial and rational functions. Let's see here. So I posted these polynomial and rational functions, part 1. What I said I would do is I'll just kind of, wherever we get to today, that's where I'll chop it off, and then I'll make a part 2, but it'll be all of these notes again. So it doesn't matter. Okay, so I guess let's take a 5-minute break until 9 o'clock, and I'll pause this recording, and then we'll come back fresh. Okay, we're back. So we're going to start with quadratic functions and models. We've already seen quadratics, right? Quadratics have this form. F of x is ax squared plus bx plus c, as long as a is not equal to 0. If a were 0 here, then you wouldn't have an x squared term, and then you're just at a linear function again, right? Bx plus c, which has the same type of shape as mx plus b, right? So we've talked about linear functions already, and so now we're going to talk more about quadratic functions. We dealt with the quadratic function when we had to factor quadratics, right? Because I thought it would be useful for you to know the quadratic formula, right? So we know how to factor a quadratic using the quadratic formula. Let's see here. You know what? Just copy that whole thing. That whole chunk. Start on a fresh page here. Okay, so we're going to be talking about polynomials. Polynomials in general can have an nth degree. So the degree of the polynomial is the highest power of x, which I think we mentioned before. So a quadratic is anything that has this type of form, right? So as soon as the highest power is x squared, then you have a quadratic. B can be 0, C can be 0, but you'd have a quadratic if you have an x squared. So we've seen quadratics before. We have seen quadratics before when we used the quadratic formula, right? When we used the quadratic formula, which is x is negative b plus minus the square root of b squared minus 4ac over 2a, to factor a quadratic, right? This tells us the zeros, right? What values of x make this thing equal to 0. Then we use those values to factor the quadratic and said, so if our zeros are plus minus 2, for example, then our factors, or -2 and plus 3, let's say, then our factor would be x plus 2 and times x plus 3. Let me write that down. Example, if we found x equals -2 and 3, then our factor are x plus 2 times x minus 3, right? Because if you plug in, so the whole goal was to, if I plug this in here, I should end up at 0. If I plug this in here, I should end up at 0. 0 times a value is just 0. So that was way back in 1.5. We didn't really spend a lot of time in 1.5. This is the only thing that I kind of got you to take away from 1.5. It was really the only thing that we needed from 1.5. Today we're going to talk about completing the square, which is also from 1.5. So I will be stealing some notes, but these notes that we're writing here will have everything that you need. So whether you're referencing, I'll kind of make it clear where I grabbed stuff from. All right, so let's see here. We already know the general shape of a quadratic. A quadratic is x to the power of 2, and we've already talked about graphing in the sense that, okay, well, the highest power of x, that dictates the general shape of this thing. So a quadratic is only going to be x to the power of 2 and then plus something times x plus some constant, right? So these quadratics are always going to be parabolas. So what's nice, or maybe not nice, we'll see how you feel in a bit. What's nice is that a quadratic function can be expressed in standard form. So notice how I'll show you how to rewrite this into standard form by completing the square. So that's where we need to bring in completing the square. Might sound familiar, maybe from a different math course, but we'll go through it. And the graph of f is a parabola with a vertex hk, where h is from here and k is from here, right? So the benefit of rewriting it in standard form as opposed to the general form is that you're easily able to find the vertex. The vertex of a quadratic is either the minimum or the maximum, depending on it, if it's facing up or facing down, right? And so just a couple of things to keep in mind is the parabola opens up if a is greater than 0. So if you have a positive a, then it's going to be up like this, making the vertex a minimum, right? Whereas if a is less than 0, then you've got a parabola like this, and then the vertex, which is the kind of the tip of it, is going to be the maximum of that function. Right, so it depends. So we get a lot of information from the vertex, so it's really useful to be able to find it and figure out what it is using the standard form. It's also a good exercise in completing the square and, again, algebra. So all quadratic functions our parabolas. Okay, that's kind of the takeaway here. And so when I say we have to complete the square, completing the square, oops. I'll underline it here. Whee. Is from 1.5. So the note's from 1.5. So completing the square, I'll go grab that little blurb, if I can. I think it might be over here. Nope. Here. Completing the square can be kind of weird when you start, okay? But the whole goal is to be able to write something nice and compact like this. So x plus b over 2, whatever b is, squared. So if you have to make something that's x squared plus bx, notice that there's no plus c, and we'll deal with that in a little bit. A perfect square, you have to add b over 2 squared to this equation, right? We can't just add things willy-nilly, right? So what we'll do is we'll add b over 2 squared as well as subtract b over 2 squared. That way we're adding nothing, right, technically. But then we'll be able to kind of regroup some stuff and rewrite this portion as a perfect square. So this here is a perfect square because everything is inside the square. Okay, so here I'll just make a note. So not x squared plus bx plus c, right? That plus c is going to be separate. So what we're going to do is we're kind of going to cut off the plus c and kind of keep it off to the side and then deal with that. And then we're going to complete the square to get it into this form, right? The a might come out front, a might be 1, x minus h squared, right? So this b over 2 would be our h, right? Or negative h because it's negative. And then our k is going to be everything that's left over. So it is nice and fun to see that, okay, if we're able to rewrite this in standard form, then we're easily be able to pick out the vertex. What I want you to be doing though as well is in Desmos, you can graph these things and you can easily find the vertex of a parabola. And so, but it's more the math that I'm interested in, right? I'm not interested in just the vertex. I want to see how you found the vertex. So let's see here. So completing the square, what I'm going to do, because when I do things with just the variables, sometimes it confuses a lot of people, especially because h and k are going to be lumps of different variables. So what I want to do is I'm just going to do some of these problems right off the bat. So here, let's just do some of these. Bring them in. So what we have to do is we're given some sort of quadratic function. First thing we're going to do is express f in standard form. So that's where we have to get into completing the square, and that's where we're going to kind of see how that works. Then we're going to find the vertex and the x and the y-intercepts of f. Then we're going to sketch a graph which will help us find the domain and range of f. The sketching part I'm just going to do in Desmos, but you definitely could, just knowing all of these pieces, you could plot it out, but that part I'll just skip to Desmos and graph it in Desmos. I guess we could sketch something. All right, let's start nice and easy. All right, let's do 9. So f of x is x squared minus 2x plus 3. So what I'm going to do is I'm going to rewrite this thing, and I want to morph it to look something like this, right? Okay, which means I have to, so by completing the square. So to complete the square, what I have to do is I have to deal with x squared plus bx on its own. So here, I'm going to write x squared minus 2x plus 3. And even though these brackets don't do anything, I'm saying, hey, I'm going to deal with this thing on its own. Then what I'm going to do is, well, first, I guess write in standard form. Okay. I think that was part A. Yeah. Okay. So knowing nothing about where to go next, it says, okay, well, to complete the square, what I have to do is I have to add b over 2 squared to this thing. If I'm adding it, I also have to subtract it, right, to keep things neutral. So I can't alter this thing or the meaning of this thing. So x squared minus 2x plus, and then b in this case is negative 2. So plus negative 2 over 2 squared. So here what I'm doing is plus b over 2 squared. Okay. And then minus negative 2 over 2 squared. Here, minus b over 2 squared. Okay. Then I'm going to put this bracket over here, and then don't forget about that plus 3. Okay. All right. So here, now I'm going to redistribute these brackets because now, let's see here. Adding 0, that's the whole point, right? If I have to add b over 2 squared, I also have to subtract b over 2 squared. Otherwise, I'm altering it, right? So here, I'm just making a note, okay, I'm adding 0, technically, right? So everything is safe. But now, this here is a perfect square. Okay. This bracket here isn't actually doing anything because there's nothing outside. So what I can do is I can shift this bracket here. I can also simplify. Negative 2 divided by 2 is, of course, negative 1, and then negative 1 squared is just 1. And same thing here. So what I'm going to do is I'm going to rewrite this as, maybe I'll do it in 2 steps. X squared minus 2x plus 1 minus 1. Okay, but you don't want to cancel those, plus 3. Okay, just kind of rewriting this. The whole point was that we were adding 0, right? So to do 1 minus 1, would be just going back to where we started. So don't do that. Okay? Again, here we're just adding 0, but in a different way. So this x squared minus 2x plus 1, that's our perfect square. So here and here, which, okay, if we have something like this, right, we've simplified our b over 2 squared, but what we can do is we can now rewrite this as a perfect square, x plus b, which is negative 2 over 2, so x minus 1 squared. So we get x, let me see here, plus b maybe I should have kept it like this. It doesn't matter, but I have to remember that it's not going to be positive 1. It's going to be x minus 2 over 2, or in fact, I should do it plus negative 2 over 2, just to emphasize where things came from, squared. And then minus 1 plus 3. So this here, right, this is now our perfect square. Okay. So we get x minus 1 squared, and then minus 1 plus 3 plus 2. Okay. Just to check my work, right? Check your work by expanding. Expanding, at least for me, expanding is way easier, right? I'm just expanding this thing out and just making sure that what I landed on here, right? This is our first time completing the square, and so what I landed on here should be equal to x squared minus 2x plus 3. Right? So I'm just going to check my work. So x minus 1 times x minus 1. Make sure x minus 1 squared is x minus 1 times x minus 1, and then plus 2. So I get x squared minus x plus 1 plus 2. So that's x squared minus 2x plus 3, which I'm hoping it is, right? So what we can say then is, okay, well, this is good to go. Whee! So x squared minus 2x plus 3 is equal to x minus 1 squared plus 2. This is what we call, here, this is the general form. And this is the standard form. Okay. From the standard form, right? So that was part A of the question that we're doing, right? So here, okay, we've landed on the standard form of this thing. Now, from our little blurb, here, okay, we've got something in the standard form. A in our case is 1, H is 1, and K is 2. Okay. So from here, right, we know the vertex is at HK. Okay. What I'm going to do is I'm just going to steal this. I'll write it down. So the standard form is A times x minus h squared plus k. Okay. in our case, A is 1. Right? Notice that there is a minus here and a minus here. If you had x plus 1 in here, then h would have to be negative 1, right? So you want to be really careful. And then our k is 2. So where a is 1, h is 1, and k is 2. So the next step here in the question, okay, so express f in standard form, we did, all right? Find the vertex and the x and y intercepts of f. So we'll start with the vertex, and then we'll talk about, we already know the x and y intercepts. The x-intercepts are where it crosses the x-axis, so where y is 0, and the y-intercepts are where it crosses the y-intercept, which is where x is 0, right? So we're going to start with finding the vertex, right? The vertex is at hk. So now that we have h and k, it's really easy to find the vertex. So B, the vertex is at hk, which in our case is at 1, 2. Remembering that even from the start here, A is positive. So A is positive means that it's going to be pointing upwards, right? So the vertex, this 1, 2, if that's the vertex at the very bottom, well, then that's the minimum value of this function, right? So here, what we can add is that since A is greater than 0, right? So A was positive 1 here, and here, right? A is 1. You know what? I'm going to say that here. Since A equals 1 is greater than 0, we know our parabola is facing up. So the vertex is a minimum. So the vertex is a minimum. That's a good start, right? We know where this thing has its bottom, right? So as a little kind of check-in point, well, if the vertex is at 1, 2, so when x is 1 and y is 2, and it's pointing up, are you going to have any x-intercepts? No, right? Because it never goes back over the x-axis. So, so just keep that in mind. So let's find, what was the x-intercepts? Well, the x-intercepts, right, are when the y is equal to 0. So this is where y equals 0. You can use this one if you want to. Use the quadratic formula. Maybe that's easiest, right? I was going to try to use this one, 0, -2. That might be good. So here, you've got a couple of options for the x-intercepts. The x-intercepts is what we find when we use the quadratic formula. So you've got some options here. Can use the quadratic formula on the general equation to find the values of x, or what I'm going to do is I'm going to say, well, y equals And now I'm going to use the standard form, x minus 1 squared plus 2. Okay. Forcing y to be 0, right? Because it's where y equals 0. So now I'm going to have 0 equals x minus 1 squared plus 2, and then solve for x. Okay. All right, solving for x, no big deal, right? Subtract 2 from both sides, so I get to negative 2 is x minus 1 squared. Oops. To undo that square, I have to take the square root. Hold up, square root of a negative number, we can't do that, right? And so there are no x-intercepts. So negative 2, the square root of negative 2 is x minus 1. Maybe I'll use red. But since we can't take the square root of a negative number, the square root of a negative, we know there are no x-intercepts. Okay. So that can happen, that's totally fine. That's if the parabola is above the x-axis or below the x-axis if it's pointing down, right? So that it can happen, and it's just something that we need to be prepared for. We did the x-intercepts, fine, there are none. Now let's do the y-intercepts. The y-intercepts are where x equals 0. Easy enough, we can just plug in x equals 0. So the y-intercepts where x equals 0. Okay. Again, it doesn't actually matter which one of these you use. Because we have the standard form, it's a little bit easier, I find, right? Plugging in x equals 0 here, but it doesn't matter. So we have y equals x minus 1 squared, let me just make sure, yeah, plus 2 at x equals 0. So now I'm going to have y equals 0 minus 1 squared plus 2. So y is negative 1 squared is 1 plus 2. So y is 3. So the y-intercept is at 0, 3. Okay. The next thing we're asked to do, so find the vertex, done. The x-intercepts, there are none, but that's okay. The y-intercepts we found. Then we're going to sketch a quick graph and confirm in Desmos. So C. Rough sketch. And then I'll say confirm using Desmos. So if we have kind of our parabola here, if this is at 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, not very good. But at 1, 2, I think our vertex was 1 and 2. Okay, so when x is 1, y is 2, and we know it's going to be facing up, which is also going to be, that helps, right? 1, 2. So this is the vertex, is at 1, 2. And then the y-intercept is at 0, 3. That is going to tell us that it's facing up, but it's just nice to be able to tell right away that it's going to be facing up by the a value. So 1, 2, and 0, 3, 1, 2, 3. Let's put that here. The y-intercept is at 0, 3. So if I had to graph this, knowing that it's a parabola, right, I want to see kind of something like that. Okay. Let's confirm this using Desmos. So whichever function you like, the general form or the standard form, we worked hard for that standard form, so I'm going to use it. I think it's x minus 1 squared plus 2. Okay. So when I graph this and I can get it to tell me what my values are, the vertex is in fact at 1, 2 and at 0, 3. What I'm going to do again here is take that original function and just make sure I get the same thing, x squared minus 2x plus 3. They are the same, so that's good, right? So we can use Desmos to confirm all our work, right? If they end up being an overlapping graph, then that's great. You found the standard form. All right, moving on, find the vertex. Confirm that it is the vertex on here, right? Find the x-intercepts. Of course, if it was facing down, we would have x-intercepts, which you can confirm. The y-intercept we're confirming, and our general sketch we're also confirming. From the sketch, right, and from Desmos, we're able to say what the domain is. So the domain for a quadratic is always going to be from negative infinity to positive infinity. Even though it looks like it's kind of, you know, tapering off, these arms, the parabolic arms, are going to keep going and going to positive and negative infinity. So the domain for these things will always be from the all real numbers. So negative 1, 2, or negative 1, negative infinity to infinity. So from here, part D, the domain is going to be from negative infinity to infinity. The range, so like I said, for all quadratics, this is the domain, right? There's no quadratic where this is not the domain. The range, however, because it'll have this vertex, it'll only go as low as the minimum and or as high as the maximum, depending on which way it's facing, right? And it can be evaluated at the vertex, so it's going to include that point. So the range in this case starts at y equals 2 and goes to positive infinity. Okay. And I'll just make a note here. Vertex is included. Okay, good. So that's also a lot of work. All of these questions are a lot of work, right? But once we've done enough of them, we've got kind of a flow going. The hardest part, I would say, is writing it in standard form. Once you have it in standard form, then you've got choices, right? You've got x squared, you've got the general form or the standard form, and you can use which one's easiest, whichever one's easiest. So let's go do one that's a little bit trickier. Let's go do 14. What we see right away is that it's facing down, right? Because you've got a negative x squared. And so it's facing down, and that changes some things, right? So we'll start with 14. We'll do 14. Put it on a fresh page here. 14 says that f of x is negative x squared plus 10x. For putting it into standard form, well, that's it's nice because we don't have that plus c, that constant in here, right? But we need to be careful because we've got a negative here, right? And so we're gonna have to pull that negative outside, which means pulling a negative out from here. So I'm factoring out a common negative. So here, Sorry, I don't know why I said B, it's A. Write in standard form. I'll make a quick note here, right? Parabola facing down. So immediately when you see this thing, you should start to think that, you know, in general, it'll look something like this. Right. And it can move up and around, and like we saw in the transformations, right? So we're just going to see where we end up at. So write this thing in standard form. Okay, so I've got negative x squared plus 10x, but I need it in the form need ax squared plus bx, right? So that means I have to have, or sorry, not a, need x squared plus bx in our completing the square, right? So what I'm going to do is I'm going to pull out this negative in front. So factor out a common negative. Negative x squared minus 10x. That's going to be really important, right? That we don't forget to pull out a negative here as well, right? And I should complete here. So need x squared plus bx to complete the square. Okay, completing the square on something like this, we said we have to add b over 2 squared. Okay. So what we're going to do is x squared plus bx plus b over 2 squared minus b over 2 squared. Okay. So we have to do that inside these brackets. So we have to be really careful. We get negative x squared minus 10x plus negative 10, because b is negative 10, negative 10 divided by 2 squared minus negative 10 divided by 2 squared. Okay. All right. Okay. So now, I didn't really give myself enough room here, but that's okay. I can rewrite this as a perfect square. Right, so here, this becomes x plus b over 2, oops, squared. Okay. So what we have in our case, right, b is negative 10, so we have to be careful. So we have that negative hanging out still outside, and then we've got x plus negative 10, negative 10 divided by 2 squared. Okay. So I've replaced this with this perfect square. And I want to show, if you wanted to go straight to -5, that's fine. I just wanted to show where it came from. But then don't forget, I have plus negative 10 over 2 squared. So inside the brackets from this negative, so minus negative 5 squared. Okay, and this is there. Okay. From here, I have negative, and then x, negative 10 divided by 2 is negative 5, so x minus 5 squared. And then I have negative 5 squared is 25, so minus 25. And actually, I don't need these big square brackets anymore. I can do kind of shorter square brackets. remembering that this negative has to get pulled inside, okay? One way or another. You can keep it outside if you want, but for this thing to be in standard form, we should bring it inside. And so this becomes negative x minus 5 squared plus 25. And now I'm in standard form. Standard form, which says a times x minus h squared plus k, right? In this case, a is -1, h is 5, and k is 25. Okay? So here, where a is -1, h is 5, and k is 25. You can check your work. I'm not going to. I'm feeling good. And also because I want to finish this question before the end of class. So the vertex here, now we're going to find the vertex. The vertex is at hk. So what's so nice about having it in standard form is that we already know where the vertex is. So it's at 5, 25. Okay. Let's think about, before we even try to figure out anything else, right? So what we expect our graph to look like, right? Our graph might look like this, right? We decided it's facing down. It's got a vertex at 525. So somewhere way up here at 525. But then it looks like it might go something like this, right? This is just what we think might happen. So I guess I could put how, not really proper, but how our graph might look. Doesn't make sense. But our graph might look like, not much better, but a little bit. So what I'm doing is I'm just checking in to see, am I expecting to have x-intercepts? Unlike before where it was facing up and we were up off the x-axis, I'm not expecting any x-intercepts. So here I'm expecting to be able to solve for x. So our x-intercepts are at, that's when y equals 0. So we can set this thing equal to 0. Can use this one. We worked hard for it, so why not? So y is negative x, oh, now I lost it, minus 5 squared plus 25. So if we set this equal to 0, we find 0 is x minus 5 squared, negative x minus 5 squared plus 25. I can subtract 25 from both sides, so I get negative 25 is negative x minus 5 squared. Divide both sides by -1 makes the negative go away, so I get 25 is x minus 5 squared. Take the square root of both sides, I get the square root of 25. Problem is, the square root, once we take it, we have to take the plus minus of the square root. So, and then is x minus 5. So it's either plus the root of 25, which is 5, or the negative of root 25, which is negative 5. So it's either 5 or negative 5, or I'll say and negative 5, is x minus 5. So solving for x is either 5 plus 5, and x is negative 5 plus 5. So x is 10 and x is 0. Both of these, right, we're going to cross the x-axis at 2 points. So it makes sense that we're going to get 2 points of x. So what this tells me is that I did a poor job drawing it here. It should go through 0, right? So I would adjust my graph a little bit, but then this is at 10. Close enough. The y-intercept is when x is 0. So y equals, and I'll use the general form, negative x minus 5 squared plus 25. So y is negative 0 minus 5 squared plus 25. And so what we have is we have y is negative 5 squared is 25. Negative 25 plus 25 is just 0. So the y-intercept is at 0, 0. Makes sense if it's going through x equals 0 for the x-intercept, right? We kind of expected that. So we can confirm this thing using Desmos, right? So our sketch might look something like, well, I know I go through 0, 0. I know I go through 10, 0. And I know my vertex is somewhere here at 525. Make sure it's more curved than that, but I'll let you confirm everything in Desmos, right? I know I'm out of time, but go through and try confirming everything in Desmos and make sure that everything looks good. But it's really nice because you can check all the steps with Desmos. Even the standard form, right? You can just plot the two, the general form and the standard form on the same graph, and if they're overlapping, they're the same. Nice. Okay, so that's pretty well it for section 3.1. So we'll start 3.2 next day, but a lot of work in there. All right. Any questions before we go? Stop this recording here.